finding out if they were conservative or not. And we had a way to check to see if a two-dimensional vector field was conservative. But we didn't have a way of checking to see if a three-dimensional vector field was conservative. Well, here it is. So we saw this back in 13.3.3, that if your field is two-dimensional, that to check to see if it's conservative, that means the field is the gradient vector field. It's a gradient vector field. It's the gradient of a scalar function. We would check this. We would need the partial of this with respect to y to be equal to the partial of this with respect to x. But it only worked in two-dimensional space. In three-dimensional space, it's pretty simple. It's pretty simple. That's it right there. That's how you can tell if a vector field is conservative. Your rotation is zero everywhere, the zero vector everywhere in the field. So you know how we were moving that thing around, it wasn't rotating? And we're like, I wonder if that's something special. Yes, that's exactly what a conservative vector field would behave like. All right? All conservative vector fields have a curl of zero everywhere in the field. So that's how you check. Divergence. All right, so that's curl, right? That's curl. Done with curl. Now let's talk about divergence. Divergence. This is the easier one to calculate. For divergence, if somebody gives you a vector field, PQR, to calculate the divergence, all you're going to do is take the partial of that with respect to x plus the partial of that with respect to y plus the partial of that with respect to z. That's it. It's a very simple computation. You're just doing three partials and adding them together. That's it. Now the notation for this is, you know how we had curl F was that del crossed with F? Here it's del dotted with F. It's really just a dot product. It's the dot product of this. If I ask you to take this right here, which is del, take that. Oops, vector, and dot it with PQR. Remember how dot products work, right? It was this times this plus this times this plus this times this. It's the same thing, but we don't have multiplication, right? We just have an operation. Partial with respect to x of p plus partial q with respect to y plus partial r with respect to z. So that's your divergence. Your answer is a number, right? A scalar. So let's, you know that field we did the curl of a second ago? Let's do that same problem. Let's calculate the divergence. So what's the divergence of this field? Well, it's this dotted with the field, which is just, the partial. So here's our P, here's our Q, here's our R. Okay, partial P with respect to what? We're doing partial P with respect to x. What is the partial P with respect to x? 2x, y, z, right? And that's it. We're not doing a vector. This is going to be a scalar. Plus, now we do the partial of this with respect to y, right? 2xy? 2xyz, sorry. 2xyz. Plus, last one, 2xyz again. And that's just 6xyz. That's it. Isn't that a little easier to compute than curl? A lot a bit easier? What's the next natural question then? We know how to compute it. It's pretty simple. Right? I introduced curl. I said, here's how you calculate it. And then I said, here's what it means, right? Now I've introduced divergence. I said, here's how you calculate it. What is it, right? What's divergence? This one, I think, is one of the coolest ideas. Let's see if I can convince you of what it is. Any questions before I move on? So for divergence, There's a couple of ways to look at it. I like this way to start. I'm going to start with this picture first. You know how earlier I had a two-dimensional vector field? I had a point in here and I had this thing with paddle wheels on it, right? What I want you to do is kind of imagine that you have your point, right? You have your point right there. But we're going to zoom in and we're going to zoom way in on that point and almost look at it like a little tiny circle, right? Okay, so we have this little tiny circle which really represents our point. And this is like, moving through, moving with the flow of the field. We already know that if it has any spin, that's called curl, right? But I want us to look at this. Consider this. If you look at this circle is almost like, what am I trying? Like a barrier, like a wall of a cell, like a cell wall, or like this room has walls, right? And so this is like a barrier around this little point. Well, the field around it has vectors everywhere, right? And there are vectors that are punching into this circle, and there's vectors that are coming out of this circle, right? There's vectors all over the place. What the divergence does is it somehow calculates how many vectors are going into that little circle and how many vectors are going out of that circle at that point. So do you agree that there's vectors from the backside going in, but then any vectors on the front edge of the circle are going out? So anything that you see in green is a vector that's going out, and anything that you see in red is a vector that's going in to the circle. I'm going to zoom in here. That's kind of a simplification of it. Do you see that we got vectors along the back edge that are punching into the little infinitesimal circle, and then you got vectors coming out. And it looks like you have about the same amount coming in as you have going out, right? The same that's coming in as going out. And the divergence measures that. And so do you see right now our divergence is 0? We have like the same amount of stuff coming into that little circle as we do going out. This has nothing to do with spinning, does it? Let me zoom back out. Now, what do you think is going to happen if I go to the right? We'll have more going in. There's longer vectors over there, right? But won't the green become long as well? So look at that. You have, I'm zooming in on it. You've got these vectors. As you move to the right along this edge, these vectors get longer, don't they? So there's like a lot going in. But then the ones on the front edge are going out too. So you look like you, again, have like a total net effect of the same amount coming in as going out, right? So look at the calculation of the divergence. It's still 0. If I move up, same. Left, same, right? It's kind of cool looking, huh? Yeah, it's kind of parabolic, right? All right, let's change the field. Oh, okay, that's a different one, right? Let me move myself back here. Go to the origin. Somewhere here. My divergence was 0 somewhere around here. There we go. That's the origin. We're at the origin right now. And you can tell like the vectors are all weird, right? There's some going in, some at different angles, right? Right now the divergence is 0. But if I move, as you saw just a second ago, if I move to the right, now my divergence is not 0. What is it? Positive 1.6. If I zoom in, do you see that you could say that you have the same amount of vectors coming in as coming out, but aren't the green ones longer than the red ones? Right? So there's more like flow out of this than there is going into it. And so that would be a positive divergence. When you think of the word divergence, what do you think of? What does that mean to you? Going away? Like if you're diverging, like if you and your best friend over the years have diverged, right? It means you've kind of gone apart. This is a measurement of things going out. Yes?
Don't we use that word in part 2?
What?
Divergence?
Yeah, this is the definition, divergence, yes.
So it's like when a graph.
We're not talking about divergence series, I think, okay.
Yeah.
So divergence is that it like goes to infinity. This divergence is more of like a measurement of how much is going out of something or into something, diverging away or coming closer, right?
Yeah.
Here, the net total effect here is that we're actually going to use this idea later. Is that if you think of this as like a little microscopic net, like a mesh net, and this is water flowing. You have more flow out than you have in. You have more going out than you have coming in. Later on, it's going to be known as flux, which is coming, all right? So we have more coming out than we have going in. So our divergence is positive. Let's move this up. I want to get a negative divergence. Okay, there we go. We've got some negative divergence. So what's happening here is that the red, the stuff going into the circle, is more than what's coming out, the green. They're longer vectors. And so your divergence is negative, all right? Now, y'all want to see this in three-dimensional space? I can do the same thing in three-dimensional space with a ball. So in three-dimensional space, I want you to look at that sphere, again, as being like this infinitesimal, it's really an infinitesimal point down there, okay? But we're zooming in on that point to make it look like a ball, and we're trying to measure the amount of stuff going in and going out along the edge of the ball. And can you tell from that picture, I've got a ton more going out than I have going in? And now I'm going to move this ball around. Watch the divergence. Whoa, now it became negative, right? There's more stuff going in than going out. So you got negative divergence. And I can actually add more vectors just to kind of show you, like, the true divergence is if you could somehow take every point, every single point along the edge of the ball. If you could somehow do that, then that's what the true divergence is. But it's really hard to show it because it would look like just a blob of red. So I can only do it for a certain number of vectors to try to convince you that there's more red than green here. So kind of cool, right? Oh, now we got positive divergence down there. Okay. Now, before this, so right here, this is the definition or the explanation. If the vector field represents the velocity of a fluid flowing through flowing fluid, then the divergence measures the tendency of the fluid to diverge or leave a point in the fluid, right? So it's like you have this point. Are things around it wanting to go away from it or come towards it? So the divergence is a measurement of that. If the divergence at a point is a positive number, then the region around that point is called a source. So think about positive divergence. Positive divergence means things want to go away from that point. So if you get positive divergence around a point, we call it a source. I think of it as like heat. You know, it's like emanating heat out. Okay? If your divergence is negative around a point, then the region around is called a sink, meaning that things are being drawn into it. Okay? That's called a sink. If your divergence is 0 at a point, then the region around it is called incompressible, because nothing wants to go in or out. It's just not compressible. All right. So there are a couple of other formulas. Do you remember the work integral right there? That integral that we did, the line integral. Let me remind you, this was really the integral from A to B. We'd have to find parametric representation of the curve first, and then it'd be f evaluated along that curve. I'll do f of r of t, and then dotted with r prime t dt. That's what that was, okay? But we said that there was another notation for this, that this was the P dx plus Q dy plus R dz. Remember that? Right? There was another way we could do that. Well, all this is saying is that if you wanted to, sorry, this is Green's theorem. Let me do something. Hold on. I'm two-dimensional. I need to be two-dimensional here because I'm doing Green's. Hold on. Right. Green's theorem says if this is a closed curve, right? If that's a closed curve, that we can do the double integral over d, right? Partial q with respect to x minus partial p with respect to y. This is last class, right? dA? Okay, that was Green's right there. That was from last class. So long as C is oriented correctly. So this right here, this piece right here, what they're trying to show you with this formula is that if you take the curl of f, what was the curl of f? Well, it's up here, way up here, right? Curl of f. Oh, right there. That's the curl of f, right? If you take the curl of f and you were to dot that with, I don't want to scroll all the way down. They're asking you to dot that with k hat. What's k hat? It's a vector. What vector is it? What's k hat? It's not I hat, it's not j hat, k hat. What's k hat? 0, 0, 1. That's k hat, right? If I ask you to dot these two vectors together, what do you get? Just the last one, right? Look at what it is. Partial q with respect to x minus partial p with respect to y. It's that, right? So what this last little formula is telling you is that, you know what, when we had Green's theorem, last class when we had Green's theorem, and we said that work integral becomes this, right? Another way to say this is that this piece right here is just the curl dotted with k. It's just a fancy way of saying what we already knew, all right? That's all. And then there's another version, which we will use next section. And then the last part of this we're not going to go into. It's just there's a bunch of identities. And you can look in your book for these identities. We're not going to use them. We're going to move on. But this would be an interesting exercise to just go through this and try and show that those two sides are true. Do you remember how you prove an identity? Start with one side, turn it into the other? Yeah. So there's a couple of exercises in this section where they do that. I'm not going to get into it. What I want to do is I want to wrap up, okay, soon here, because I know y'all came on Thanksgiving, but I want to give you all a head start on something. I'm going to have a handout for you. That's pretty much the end of that section, okay? Yes?
You know how you just showed that, how you get Green's theorem?
How what?
How you get Green's theorem?
Yes.
It was derived from that, right? Green's theorem was derived from that?
Yes, from the, okay. Yeah, it's not, it wasn't the other way around. It wasn't like we came up with Green's theorem, oh, by the way, it looks like that. It was actually the other way. Yeah. Because we're going to have another version of Green's theorem. Right now, Green's theorem requires us to live where? To use Green's theorem, where do we have to be? Two-dimensional space. There's another theorem where we can go into three-dimensional space and do the same thing. It's called Stokes' theorem. So you could look at Green's theorem as like a generalization, or as a specific instance of Stokes'. Stokes is going to come next. It's the section after 3.6. It's in 3.7. So we're almost at Stokes', and then we're at sorry, I said 13. We're almost there, and then I believe we're close to the end, but we only have 4 class meetings after this. That's it. We only meet 4 more times. So, all right, here's your handout. First thing you'll notice is that it's in color. spent some time at the color copier today. So for those of you who aren't here today, you just can, if you want a color copy, you can get it for me. Okay, so what we're going to do is, I talked about this at the end of class last time. I said we need to be able to draw surfaces. We need to be able to draw surfaces with vector functions, right? That's the way I ended class last time. This right here is a couple of examples where I give you these different surfaces and I ask you to find the vector functions that draw these. I'm going to go through the first few of these and then I'd like to leave the rest. So I'm probably going to do A, B, C, and D and leave E, F, and G to you. All right? Okay, so let's start with A. The whole idea here is what I brought up last class, is that we know that when you do R of t equals a two-dimensional vector or a three-dimensional vector, we know that this draws what? What is R of t? A vector function of a single variable that spits out either a two or three component vector. What does that draw? One variable in. A line or a curve, right? These are curves. Right? That has to be a curve. Go back to chapter 10, I don't remember what section, but we talked about space curves, how you draw curves in space. You use a vector function of one variable. What we'd like to do now is we'd like to take a vector function, we'd like to plug two inputs in it. Instead of t, we're going to plug in u and v, and it's going to spit out a three-dimensional vector only, all right? A three-dimensional vector only. And this is going to draw a surface. Okay, this will draw us a surface. So we're going to start with this example right here. Now I've given you some information about this surface. You can read the information. I'm just going to show you the picture, okay? So I did it in color because it's really hard to see when this is just grayscale, but I'm going to rotate this around to help you. So look at what it says. It says we've got this set of points, x, y, z in R3, where I say x squared plus z squared must be less than or equal to 2, and y must be 0. So what this means is this is a circle, right? This is a circle. Why have I never seen that typo before? What should that be? This should be what? Let's make this a 4. Sorry, make that a 4. I've never seen that typo before. I'm noticing a couple of typos lately. If this was an equal sign, if it was just equals, it would be what? What is that the equation of if it was an equal sign? Circle, radius, 2. In what plane though? In the xz plane, right? So you can see that here. That's what we have. We have a circle in the xz plane. You see it? It has a radius of 2. Now but not just the circle, right? It's not just the edge. It's what? Everything in it. So it's a disk, right? It's a disk. And that's why the inequality is there. The inequality is there because that tells you a circle of radius 4 and everything in between, all the way down to a point. Now what about the y being 0? Why is the y being 0 important? Well, because it's on the xz plane, right? If I said y was 1, where would it be? It would be this disk, but it would be moved out 1 on the y, wouldn't it? See that? Okay, I want us to come up with a vector function that draws this. Okay? A vector function that draws this. So I want to come up with an r of uv that will draw this. So let's talk about, is there anything about this vector function that you know for sure? For sure, no doubt, like for sure. The y is 0, right? Any point that lives on this disk, the y is 0. That's never going to change. Now, what about the x and the y? Sorry, x and the z. These points, I need to draw this disk, don't I? Now, we know how to draw circles, don't we? Cosine theta, sine theta. And then we put an r in front to adjust the radius. So I'm going to put here cosine, I can't use theta. I've got to use either u or v. So I'm going to use u, cosine u, sine u. That would draw me a unit circle. Right? This would draw me the unit circle in the xz plane. I don't want the circle, I want the disk. So I want to control the radius. Yeah, I have control over v, don't I? So I put the v in front. This is what I showed y'all last class, right? At the end? Yeah. Now we need to put below here what our restrictions on u and v are. So u is like the theta was. That's going to go from 0 to 2 pi. And my v is the adjustment of the radius, which should go from 0 to 2. Right? So, do y'all see what's happening here? The cosine u, sine u is drawing the circles. The v in front is telling you how big your circles need to be. And so the circle radius is going to vary from 0 to 2, and then the angle, of course, is 0 to 2 pi, so we draw the whole thing. Is that clear? No questions? We're done. That's it. This is the vector function. Here's the domain. All right, we need to see if we can now come up with the vector functions, plural, which give us the 4 faces of this tetrahedron. Shit, right? Oh, man. How many surfaces are there here? There's 4, right? There's, I guess, what you would call the green, I guess you can see on the bottom is like the XY plane. You got like this backside, you got that backside, and then you got the front, like, diagonal face of it, right? 4 surfaces. Let's go one at a time here. Let's see here. Let's do, which one do we want first? You want to do the ground first? No, not that one. You want to do that one right there? The one in green? Yeah, let's do that one first. We're going to do the ground first. Okay? Let's call that one S1. Now, when you label it, if you're going to draw it on your thing, draw an arrow to the bottom of it. That way, it's a little easier to see. So S1, the ground. Surface 1. Okay, surface 1. All right, when I look at that surface 1, let me kind of draw it first. For S1, what axes do I have that triangle in? It's the XY, right? XY. So X and Y. Do you know any of the points on that triangle? We have 0, 0 here, right? And yeah, this comes out on the x-axis 3, right? This is coming from the points. Y'all can see the points, right? So this is 3, 0 right here, so that's 3, and this one was 4. So we got that right there, right? Okay. That's useful information because I can look at this as being a function of x. I could say y is equal to negative 4/3 x plus 4. How did I get that equation of that line so fast? We go rise over run. So slope is negative 4/3, and then the y-intercept is 4, right? So that's the equation of that line. Okay, great. Let's see. I need to come up with a vector function, r of uv. And let's do r sub 1. Can we do that, r sub 1? Because it goes with surface 1. That way when we have all 4 of our r's, it's r sub 1, r sub 2, r sub 3, r sub 4. All right. So here's the way I'm going to do this. First thing I'm going to notice is that no matter what, if I'm on the green, the z is 0. Right? If you're on the floor, the z is 0. So there's no work to be done there. But I need to figure out the x and the y. So I have control over two variables, right? I want my x values between, what, 0 and 3? Okay, so my x here is just going to go between 0 and 3. But I'm not going to call it x. I'm going to call it, I don't know, u? You want to call it u? Now, underneath this, do you agree right now that u should go between 0 and 3? Right? So the u is just x. That's going to go between 0 and 3. Now, what about, this is the part students have some trouble with. What about the y coordinate? What can you say? The y coordinate is from here to here, right? From there to there, which will depend on the x, won't it? Depend on the x. So I have control of another variable here, don't I? So this is the part. What do I put here? What do I put in for y? What do I put? Try something. I mean, what is your instinct telling you? I have another variable, don't I? So just tell me if you think this will work. Can I put v here? Think about this. Think about this. Let me write down. And then tell you that v is between, what is our v between? V is the y, right? What is that between? 0 and negative 4/3 u plus 4. See if that makes sense to you. Let's try something. Let's say we have u, right? Let's say u is 0, okay? Because it can be between 0 and 3. If u is 0, we're right here, aren't we? And then our y component would be v. Now, what is v between? 0 and, what did I just plug in for u? 0. So it would be between 0 and 4. Is that right? Does that work? If I told you u was 0, then that would mean your v is between 0 and 4. That's what I want. That's what I want, right? And let's say u is 1. If u is 1, yeah, it's going to be harder. If u is 1, what's my v between? 0 and, if I plug 1 in here, I'm going to get some number, right? And that's actually from there to there, right? Not quite all the way up to 4. Is that doing what you want it to do? No? Okay, that's it. Here's what students will do that's incorrect. What they'll do is this. Right here, they'll put negative 4/3 u plus 4. And not even use a v.